You're moving right now, not just sitting there reading this. You're hurtling through space at over 2 million kilometers per hour towards something so massive it defies comprehension. And here's the strange part. We only discovered what we're actually moving toward a few years ago. Right now, as you process these words, Earth is spinning on its axis at roughly 1,600 kilometers per hour. That's the motion you feel as day and night, as sunrise and sunset. But that's just the beginning. Our planet simultaneously orbits the Sun at 108,000 kilometers per hour, completing one revolution every year. The movement creates our seasons, marks our calendar, defines the rhythm of life as we know it. But the Sun isn't standing still either. Our entire solar system, all 8 planets and everything gravitationally bound to our star, races around the center of the Milky Way galaxy at speeds exceeding 828,000 kilometers per hour. One complete orbit takes 230 million years. The last time Earth occupied this particular position in the galaxy, dinosaurs roamed Pangea, and trilobites had just gone extinct. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. These nested motions create something remarkable. Earth doesn't follow a simple circular path through space. Instead, we trace a complex helical pattern, spiraling within the solar system's spiral, within the galaxy's rotation. Picture a corkscrew wrapped around another corkscrew, slightly squished because the plane of our planetary orbits tilts about 60 degrees relative to the galactic plane. Most people stop here. They think this explains our cosmic motion, rotation, revolution, galactic orbit, 3 movements, each progressively larger in scale. Neat, contained, understandable. They're missing the biggest movement of all, because the Milky Way itself is moving. Not just drifting aimlessly through the void, but rushing towards something specific at 600 kilometers per second. That's 2.16 million kilometers per hour. Fast enough to cross the distance from Earth to the Moon in less than 12 minutes. What could possibly pull an entire galaxy containing hundreds of billions of stars across such vast distances? In the 1970s, astronomers noticed something odd. When they measured the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, they found an asymmetry. One side of the sky appeared slightly warmer than the other, not by much, just a few thousandths of a degree. But the pattern was unmistakable. This temperature difference revealed our motion through the universe. As we move toward one direction, the radiation from that region gets compressed, increasing its temperature. The radiation from the opposite direction gets stretched, cooling slightly. The same Doppler effect that changes the pitch of a passing siren, but applied to the oldest light in existence. The measurements told astronomers we're moving at tremendous speed. But toward what? For years, the answer remained hidden behind the Milky Way itself. There's a region of space called the zone of avoidance, a swathe of sky obscured by our own galaxy's dust and stars. It covers only about 10% of the visible sky, but that 10% happens to lie exactly in the direction we're moving. Trying to see through it is like trying to spot distant headlights through thick fog. The light is there, but the obstacles in between make observation nearly impossible. Through the 1980s and 1990s, astronomers developed clever workarounds. They used infrared telescopes to peer through the dust. They mapped radio emissions that could penetrate the obscuring material. Slowly, painstakingly, they began to construct a picture of what lay beyond. What they found was staggering. Roughly 150 to 250 million light-years away, hidden behind the zone of avoidance, sits a gravitational monster, a concentration of mass so enormous it warps the motion of galaxies across hundreds of millions of light-years. They called it the Great Attractor. The name fits. This isn't just a large galaxy or even a large cluster of galaxies. It's a focal point where matter has been accumulating for billions of years. The Great Attractor contains a mass equivalent to tens of thousands of Milky Way galaxies, all concentrated in a relatively small region of space, and it's pulling us toward it. Every second, we move 600 kilometers closer. Every hour, over 2 million kilometers. Every day, we travel roughly 50 million kilometers toward this gravitational focal point. The journey has been ongoing for billions of years. We're still hundreds of millions of light years away, but we've been falling toward it since long before Earth formed, before the sun ignited, before our solar system existed at all. By the late 1990s, intense observational campaigns identified the Norma cluster at the center of the Great Attractor region. Here was concrete evidence, not just theoretical calculations or inferred mass distributions, but actual galaxies, thousands of them, crowded together in one of the densest regions of the local universe. But here's where the story takes its first strange turn. The Great Attractor, as massive as it is, can't fully explain our motion. The math doesn't work. Astronomers calculated how fast the Milky Way should be moving based on the Great Attractor's mass. The answer came up short. Something else, something even more massive, must be influencing our trajectory. They found it in 2014. Researchers analyzing galaxy motions across the local universe discovered that the Great Attractor isn't actually our final destination. It's more like a waypoint, a gravitational landmark along a much longer journey. Both the Milky Way and the Great Attractor itself are moving towards something far larger. We're part of a supercluster, a collection of galaxy groups and clusters spanning 500 million light-years, containing roughly 100,000 galaxies. The researchers named it Laniakea, from the Hawaiian words meaning immense heaven. The name honors Polynesian navigators who used their knowledge of the sky to cross vast ocean distances, appropriate for a structure that defines our cosmic address on the largest scales. Within Laniakea, galaxy motions follow predictable patterns. Matter flows inward toward the center of mass, like water flowing downhill toward a valley. The Great Attractor marks the deepest part of that valley, the point where all the gravitational streams converge. It's not pulling us through some mysterious force. We're simply following the natural contours of space itself, shaped by the distribution of mass throughout the supercluster. This discovery fundamentally changed how astronomers think about cosmic structure. Laniakea isn't held together by gravity the way a galaxy or even a galaxy cluster is. It's too large for that. The universe's expansion, driven by dark energy, works against gravitational binding on these scales. Instead, Laniakea represents a temporary configuration, a snapshot of structure in a universe that continues to evolve. In fact, Laniakea is projected to be torn apart over cosmic time. Dark energy, that mysterious component that makes up roughly 68% of the universe's total energy density, will eventually overcome the gravitational attraction holding the supercluster together. Billions of years from now, the galaxies within Laniakea will be scattered across an even larger volume of space. But that's billions of years away. For now, we're still falling inward, still riding the gravitational currents that flow through our cosmic neighborhood. Or so astronomers thought, because in 2017, something unexpected emerged from the data. While studying the peculiar velocities of galaxies, the deviations from the uniform expansion of space, researchers identified a second major influence on our motion, not an attractor this time, but a repeller. The dipole repeller, as they named it, lies roughly 717 million light-years away in the opposite direction from the Shapley supercluster. It's not actually pushing us away through some repulsive force. Instead, it represents a vast underdensity, a region of space with far less matter than average. Think of it as a cosmic void. Here's what makes it fascinating. While the Shapley supercluster pulls us toward it, through its immense gravity, the dipole repeller appears to push us away. The push isn't real in a physical sense. It's an illusion created by the absence of matter. In a void, there's nothing to gravitationally attract nearby galaxies. Meanwhile, the denser regions surrounding the void pull matter away from it. The net effect looks like repulsion, even though it's really just the absence of attraction. The discovery of the dipole repeller revealed something profound. Our motion through space isn't determined by a single massive structure pulling us in one direction. We're being both pulled and pushed, attracted toward dense regions, while simultaneously moving away from empty ones. The cosmic microwave background dipole, that temperature asymmetry astronomers first measured in the 1970s, results from both influences contributing roughly equally. We're not just falling towards something, we're also fleeing from nothing. This dual influence shapes the motion of our entire galactic neighborhood. The local group, our small collection of galaxies including the Milky Way, Andromeda, and about 50 smaller galaxies, moves relative to the cosmic microwave background at 631 kilometers per second. That's over 2 million kilometers per hour, faster than our orbital speed around the galactic center. The direction? Toward galactic coordinates of longitude 271.9 degrees and latitude 29.6 degrees. For reference, that's roughly toward the constellation Crater, near its boundary with Leo. If you could see the cosmic microwave background with your eyes, you'd notice it appears slightly warmer in that direction and slightly cooler in the opposite direction. But even this description simplifies the reality, because recent measurements suggest something even stranger might be happening. In November 2025, researchers at Bielefeld University published findings that challenge our understanding of cosmic motion. According to their analysis of radio galaxy distributions, our solar system might be moving more than 3 times faster than previously thought. Not the 828,000 kilometers per hour we calculated from galactic rotation, but speeds approaching 2.5 million kilometers per hour. If confirmed, this would require a fundamental reassessment of cosmological models. Either there are unknown systematic errors in how we measure galactic distances and motions, or the distribution of matter in the universe differs significantly from current models. Both possibilities carry profound implications. The excess velocity, if real, reaches statistical significance at the 5.4 sigma level. In particle physics, 5 sigma represents the gold standard for claiming a discovery. The dipole direction matches the cosmic microwave background measurements within 5 degrees, suggesting the signal is genuine rather than an artifact of measurement error. Yet Planck's satellite measurements of the cosmic microwave background imply our motion should be around 827,000 kilometers per hour. That's the benchmark against which all other measurements are compared. If galaxy surveys show us moving 3 times faster, something doesn't add up. Perhaps the distribution of radio galaxies isn't as uniform as assumed. Perhaps there are selection effects in which galaxies we can observe and which remain hidden. Or perhaps our fundamental assumptions about large-scale cosmic structure need revision. The answer matters because it determines whether we truly understand the universe's largest structures. The cosmic web of galaxies, the filaments and voids that stretch across billions of light years, follows patterns predicted by our best cosmological models. Those models rest on assumptions about how matter clumps together under gravity, how dark matter shapes structure formation, how dark energy influences expansion. If our local motion deviates significantly from predictions, it suggests those assumptions might be incomplete. This brings us back to the zone of avoidance, that frustrating blind spot in our view of the cosmos. Despite decades of observations using every available wavelength, roughly 10% of the sky remains difficult to study. That 10% coincides with major mass concentrations, including the Norma and Vela superclusters, structures that significantly influence local galactic motions. Recent surveys using radio telescopes to detect neutral hydrogen have begun mapping this region with unprecedented detail. One study discovered 719 galaxies within the Vela cluster alone, less than a third of which had been previously known. Each new discovery refines our understanding of the mass distribution shaping our cosmic trajectory. But there's something else hidden in that direction, something that makes the great attractor look small by comparison. The Shapley supercluster sits 650 million light-years away in the constellation Centaurus. It contains more than 8,000 galaxies, with a combined mass exceeding 10 million billion suns. That's not a typo. 10 million billion solar masses concentrated in a region that represents the single largest concentration of matter in our local universe. And we're falling toward it. Not just the Milky Way, the entire Laniakea supercluster, all 100,000 galaxies, including the great attractor itself, is being drawn toward this cosmic behemoth. The great attractor isn't the end point of our journey. It's a waypoint, a gravitational tributary feeding into something far more massive. This creates a hierarchy of motion that staggers the imagination. Earth orbits the Sun. The solar system orbits the galactic center. The Milky Way falls toward the great attractor. The great attractor, along with everything else in Laniakea, streams toward the Shapley concentration. Each level of this cosmic cascade operates on timescales that dwarf human comprehension. Astronomers call the Shapley supercluster a basin of attraction. Picture water flowing across a landscape, following valleys and channels toward the lowest point. Galaxies behave similarly, flowing along gravitational gradients toward concentrations of mass. The Shapley Basin dominates local cosmic geography like a massive depression in the fabric of space-time, pulling everything within hundreds of millions of light-years toward its center. But here's what makes this discovery particularly unsettling. We only learned about the Shapley supercluster's dominance in the late 1980s. For decades, astronomers assumed the great attractor represented the ultimate destination. Then better surveys revealed structures beyond it, and the picture changed completely. What else might we be missing? The zone of avoidance doesn't just hide individual galaxies, it obscures entire superclusters. The Norma and Vela superclusters, both significant contributors to local gravitational flows, sit squarely in this blind zone. Recent radio surveys have begun penetrating the obscuring dust, revealing galaxy concentrations that were completely unknown until the past few years. Each new discovery forces recalculation of the mass distribution shaping our trajectory. Every hidden supercluster adds gravitational influence that alters predictions about where we're headed and how fast we're moving. The cosmic map keeps expanding in directions we couldn't previously observe. This brings us to one of the strangest revelations in modern cosmology. Something discovered in 2017 that fundamentally changed how we understand cosmic motion. We're not just being pulled, we're also being pushed. The dipole repeller sits approximately 717 million light-years away, in the opposite direction from the Shapley attractor. It's not a concentration of mass. It's an absence, a supervoid so vast and empty that it creates what appears to be a repulsive force. Wait, how can emptiness push? It doesn't, not directly. The mechanism is more subtle. Imagine standing between two magnets. One powerful magnet pulls you strongly from the front. Behind you, there's nothing. No magnet, no force, just empty space. You accelerate toward the strong magnet, but you're also effectively being pushed away from the emptiness behind you because there's nothing there to hold you back. The dipole repeller works on this principle, but with gravity instead of magnetism. Matter everywhere around this supervoid gets pulled toward dense regions like the Shapley concentration. This drains mass from the void, making it progressively emptier. Galaxies between the void and the dense regions experience stronger gravitational pull from one side than the other, creating an apparent repulsion from the underdense region. The discovery paper showed something remarkable. The dipole repeller and the Shapley attractor contribute roughly equally to the cosmic microwave background dipole. That observed motion of 600 kilometers per second toward the constellation crater. Half comes from being pulled toward Shapley. Half comes from being pushed away from the void. You're being squeezed between cosmic forces, operating on scales of hundreds of millions of light years. But even this picture, as strange as it sounds, simplifies reality. Because in March 2026, computer simulations revealed another hidden structure that's been influencing galactic motion all along. Our galaxy sits in a gigantic flat sheet of matter, dominated by dark matter. This sheet extends tens of millions of light-years in 2 dimensions, but remains relatively thin in the third. Above and below this sheet lie enormous voids, regions of space nearly devoid of galaxies and matter. Astronomers call it the local sheet. You live in a cosmic pancake. This structure explains something that had puzzled researchers for decades. Galaxies just beyond the local group move in ways that didn't match predictions. They drift outward when they should be falling inward toward our gravitational pull. The local sheet resolves this paradox. For galaxies embedded in the sheet, gravitational forces balance in unexpected ways. The local group pulls them inward, yes, but mass distributed throughout the rest of the sheet pulls them in other directions. The deep voids above and below the sheet mean there's no gravitational pull from those directions. The combined effect allows nearby galaxies to drift outward along the plane of the sheet rather than falling toward the local group. Dark matter makes this structure possible. Visible galaxies trace the outline, but dark matter provides the gravitational scaffolding that holds the geometry together. The sheet contains roughly 10 times more dark matter than ordinary matter, creating gravitational fields that shape galactic trajectories in ways invisible to our telescopes. This discovery emerged from analyzing peculiar velocities. That term sounds exotic, but it simply refers to how galaxies move relative to the Hubble flow. According to Hubble's law, galaxies recede from us at speeds proportional to their distance. The universe expands, carrying galaxies along like raisins in rising bread dough. But galaxies don't just ride the expansion, they also move relative to it, pulled by local gravitational fields. These peculiar velocities reveal the distribution of mass in the universe. By measuring how galaxies deviate from pure expansion, astronomers can map the gravitational landscape they're moving through. Recent surveys have traced peculiar velocities across vast distances, revealing what researchers call bulk flows. Entire regions of space spanning hundreds of millions of light-years move coherently, flowing like cosmic rivers toward concentrations of mass. One recent analysis found bulk flow velocities of 315 kilometers per second at distances of 150 megaparsecs, roughly 500 million light-years. These flows aren't random turbulence. They're organized streams following the gravitational contours of the cosmic web. Galaxies flow along filaments toward nodes where superclusters form. They drain from voids like water flowing downhill. The patterns reveal structure in the universe's mass distribution that extends to the largest observable scales. But there's something else lurking in the data. Something astronomers are still trying to understand. In certain directions, the measured bulk flows seem stronger than cosmological models predict. The universe appears lumpier than it should be, with mass concentrations creating gravitational influences that extend farther than expected. This could indicate problems with our cosmological models. Or it could mean there are structures beyond our current observational limits that we haven't accounted for yet. The South Pole Wall hints at such structures. Discovered through analysis of peculiar velocities, this enormous filament of galaxies wraps around the Laniakea supercluster like a cosmic arm. Its densest concentration sits 500 million light-years away in the direction of Earth's south celestial pole. But the structure extends in a great arc, spanning 200 degrees across the sky. Parts of the South Pole Wall come as close as 300 million light-years, making it one of the largest structures in our immediate cosmic neighborhood. Yet it went undetected until recently because it lies partially behind the zone of avoidance and partially in directions that required careful velocity surveys to identify. Galaxies along the South Pole Wall move slowly toward the south celestial pole, then across portions of sky obscured by the Milky Way, eventually flowing toward the Shapley concentration. The wall acts like a highway, channeling galactic traffic along its length toward the dominant mass concentration in the local universe. Astronomers wonder if the mapped portion represents only a fraction of the full structure. The survey data extends only so far. The South Pole Wall might continue beyond currently observed regions, potentially connecting to other large-scale structures we haven't identified yet. This uncertainty highlights a fundamental challenge in modern cosmology. We can only observe what our instruments can detect and what isn't hidden behind foreground structures. The zone of avoidance blocks 10% of the sky. Distance limits prevent us from seeing the faintest, most distant galaxies. Survey boundaries constrain how far we can trace structures before running out of data. We're mapping the cosmic web with incomplete information, like cartographers charting a continent after exploring only the coastal regions. Each new survey extends our reach, but vast territories remain unexplored. This brings us back to that November 2025 study suggesting our solar system might be moving 3 times faster than expected. If confirmed, the implications cascade through multiple levels of understanding. First, it would require reassessing the mass distribution in the local universe. Faster motion implies stronger gravitational pull, which means more mass than currently accounted for. That mass might be hiding in the zone of avoidance, or distributed differently than models assume, or existing in forms we haven't properly considered. Second, it would challenge our understanding of cosmic structure formation. Current models predict how matter clumps together under gravity over billions of years. These models successfully explain many observed features of the universe, from the cosmic microwave background fluctuations to the distribution of galaxies on large scales. But they rest on assumptions about dark matter, dark energy, and the initial conditions after the Big Bang. If local motions deviate significantly from predictions, it suggests those assumptions might be incomplete. Perhaps dark matter behaves differently than theorized. Perhaps dark energy varies across space rather than remaining constant. Perhaps the initial conditions contained asymmetries we haven't accounted for. Third, it would raise questions about the uniformity of the universe. Cosmological models assume the universe looks roughly the same in all directions when viewed on sufficiently large scales. This principle, called isotropy, underpins much of modern cosmology. Large deviations from predicted motions could indicate violations of this principle, suggesting the universe has preferred directions or contains structures that break the assumed symmetry. The 5.4 sigma significance of the measurement makes it difficult to dismiss as statistical noise. In particle physics, 5 sigma represents the threshold for claiming a discovery. Finding such strong deviation from expected values demands explanation. But the measurement relies on surveys of radio galaxies, and those surveys have their own limitations. Selection effects might bias which galaxies appear in the sample. Distance measurements to individual galaxies carry uncertainties that could accumulate into systematic errors. The distribution of radio galaxies might not perfectly trace the overall matter distribution. Resolving the discrepancy requires additional data, more surveys, covering more galaxies, using different techniques. Comparison between multiple independent measurements to identify systematic errors or confirm genuine anomalies. This process takes time, often years, as new instruments come online and existing surveys expand their coverage. Meanwhile, we keep moving. Earth continues its complex dance through space, spinning on its axis while orbiting the Sun, which orbits the galactic center, which falls toward the great attractor, which streams toward the Shapley concentration, all while being pushed by the dipole repeller and channeled along the local sheet. Each motion occurs simultaneously, creating a trajectory through space-time that defies simple visualization. You're not traveling in a straight line. You're not even traveling in a simple spiral. You're following a path that curves in multiple dimensions simultaneously, responding to gravitational influences, operating on scales from planetary to cosmic. And here's what makes it truly strange. That path is changing, not just following a predetermined course, but actively evolving as the universe expands and structures continue forming. The gravitational landscape around us isn't frozen in time. It's a dynamic system where mass distributions shift, cosmic structures evolve, and the forces acting on our galaxy change magnitude and direction. 4 billion years ago, the great attractor exerted different influence than it does today. 4 billion years from now, assuming we're still around to measure it, the gravitational architecture of our local universe will have transformed again. This evolution happens because gravity works slowly but relentlessly. When you see a galaxy cluster today, you're observing a snapshot of an ongoing process that began billions of years ago and will continue billions of years into the future. Galaxies don't just fall into clusters and stop. They interact, merge, rearrange themselves under mutual gravitational influence. The cluster grows more massive, its gravitational reach extends farther, and it begins affecting galaxies that were previously too distant to feel its pull. Scale this up to superclusters, and the picture becomes even more complex. Laniakea isn't a permanent structure, it's a temporary gathering of galaxies that will eventually disperse as dark energy drives cosmic expansion. But before that happens, the supercluster will continue evolving. Galaxies will keep falling toward the great attractor. Some will merge with others. New clusters will form from the accumulation of smaller groups. The overall shape and mass distribution will shift. This creates a feedback loop. As mass accumulates in certain regions, those regions exert stronger gravitational pull, which draws in more mass, which increases the gravitational pull further. The process reinforces itself until dark energy's repulsive effect becomes dominant, at which point expansion wins and the structure begins to tear apart. We're living through the middle chapters of this story. Laniakea has been forming for billions of years, and it will persist for billions more before dark energy overcomes its gravitational coherence. But during our epoch, the structure is still actively assembling. Galaxies are still falling inward. The great attractor is still attracting. And beyond Laniakea, the Shapley concentration follows the same pattern on an even larger scale. It's pulling in not just individual galaxies, but entire superclusters. Laniakea itself, containing 100,000 galaxies spread across 500 million light-years, is falling toward Shapley like a leaf caught in a river current. This hierarchical organization extends to the largest scales we can observe. Superclusters cluster into even larger structures. These structures align into vast filaments and sheets separated by enormous voids. The entire observable universe resembles a cosmic web, with matter concentrated along interconnected strands surrounding empty regions. Your position within this web determines your motion. Galaxies in dense filaments experience strong gravitational acceleration toward nearby clusters and superclusters. Galaxies near voids feel weaker attraction and sometimes appear to be repelled as surrounding matter drains away toward denser regions. The cosmic web channels galactic motion like valleys and ridges channel water flow. The dipole repeller demonstrates this channeling effect perfectly. It's not actually pushing anything. It's simply a region where matter has drained away so thoroughly that galaxies on its edges preferentially move toward the denser regions surrounding it. The void becomes deeper as more matter leaves, which makes the apparent repulsion stronger, which accelerates the draining process. Voids grow just as clusters grow through opposite mechanisms. Clusters accumulate mass and become denser. Voids lose mass and become emptier. Both processes stem from the same gravitational dynamics operating on different initial conditions. This brings us to a crucial question. How did those initial conditions arise? Why does the universe have this web-like structure instead of being uniformly distributed or completely random? The answer traces back to the earliest moments after the Big Bang. Quantum fluctuations in the infant universe created tiny density variations, regions slightly denser or slightly less dense than average. These variations were microscopic, differences of 1 part in 100,000 or less, but they were enough. As the universe expanded and cooled, those tiny overdense regions began attracting nearby matter through gravity. The underdense regions lost matter to their denser neighbors. Over billions of years, this process amplified the initial tiny fluctuations into the massive structures we observe today. Regions that started out 0.001% denser than average became galaxy clusters. Regions that started 0.001% less dense became voids. The cosmic microwave background preserves a record of those primordial fluctuations. When we map its temperature variations across the sky, we're seeing the seeds of all cosmic structure frozen in time from 380,000 years after the Big Bang. The slightly warmer spots in that map correspond to regions that would eventually become galaxy superclusters. The slightly cooler spots mark what would become voids. Cosmologists can trace the evolution from those early seeds to present-day structures using computer simulations. They start with the observed cosmic microwave background pattern, apply the laws of gravity and fluid dynamics, and let the simulation run forward through billions of years of cosmic time. The results match observed large-scale structure remarkably well. Simulated universes develop filaments, clusters, and voids in the same proportions and configurations we see through telescopes. This success validates our understanding of cosmic structure formation. The web-like architecture of the universe emerges naturally from simple initial conditions, plus gravity plus dark matter plus dark energy. No special fine-tuning required. Just let the physics run its course. But here's where it gets interesting. Those simulations make specific predictions about how fast structures should be growing and how quickly matter should be flowing through the cosmic web. When we measure actual galaxy velocities and compare them to simulated predictions, we usually find good agreement. Usually. The Bielefeld study suggesting our motion might be 3 times faster than expected would represent a significant deviation from those predictions. If confirmed, it would mean either the simulations are missing something or our measurements contain systematic errors. Both possibilities deserve serious investigation. The simulations assume certain properties for dark matter and dark energy. If those assumptions are wrong, the simulations would produce incorrect predictions for galactic motions. Our measurements rely on distance estimates to individual galaxies, which carry uncertainties that could accumulate into systematic biases. Sorting this out requires patience and careful analysis. Science doesn't advance through single dramatic discoveries that overturn everything. It advances through gradual refinement as better data constrains theories more tightly and reveals where those theories need adjustment. Meanwhile, the motion continues. Every second, Earth travels 370 kilometers toward the great attractor. Every hour, we cover more than 1 million kilometers. Every day, nearly 32 million kilometers. In the time it took you to read from the beginning of this section to here, Earth moved roughly 100,000 kilometers through space in its combined motion toward these distant gravitational sources. You can't feel this motion. Evolution didn't equip us with organs to sense our movement through the cosmic web. We evolved to sense motion relative to Earth's surface, not motion relative to the cosmic microwave background rest frame. Our vestibular system detects acceleration when we change speed or direction, but constant velocity motion produces no sensation regardless of how fast we're traveling. This is fortunate. If we could sense our cosmic motion, the experience would be overwhelming. You'd feel yourself spinning at 1,600 kilometers per hour from Earth's rotation, while simultaneously being hurled at 108,000 kilometers per hour around the Sun, while simultaneously racing at 828,000 kilometers per hour around the galactic center, while simultaneously plunging at over 2 million kilometers per hour toward the Shapley concentration. The combined sensation would be incomprehensible. Instead, you sit comfortably reading these words, blissfully unaware of your breakneck journey through space. The cosmic motions happen on scales so vast they become imperceptible at human scale, just as Earth's curvature becomes imperceptible when you're standing on its surface. But imperceptible doesn't mean inconsequential. These motions shape our cosmic neighborhood and will determine the future configuration of the local universe. The galaxies falling into Laniakea today will merge and interact over the coming billions of years. Some will collide, triggering bursts of star formation. Others will gravitationally strip gas from each other, quenching star formation and transforming spiral galaxies into ellipticals. The great attractor region will become increasingly crowded and violent as more mass accumulates. Eventually, assuming dark energy maintains its current properties, the expansion of space will overcome these gravitational attractions. Laniakea will stop accreting new galaxies. The infall will reverse. Superclusters will begin dispersing as expansion drives them apart faster than gravity can hold them together. This transition won't happen suddenly. It's already occurring on the largest scales, where galaxy groups separated by more than a few 100 million light-years are receding from each other faster than gravity can pull them together. Laniakea exists in a middle ground, where internal gravitational binding is still stronger than expansion, but that balance is temporary. In perhaps 100 billion years, give or take, the local universe will look radically different. Laniakea will have dispersed. The Milky Way and Andromeda, assuming they've merged as predicted, will be isolated in an increasingly empty region of space. Distant galaxies will have receded beyond observation as their light redshifts into undetectability. Future astronomers, if they exist, will inhabit a universe that appears far emptier and more isolated than the one we observe today. But they'll still be moving. Even after Laniakea disperses and the great attractor loses its influence, whatever merged galaxy descends from the Milky Way will continue moving through space. The motion will have different causes, responding to different gravitational influences, but it will persist. Motion is fundamental to existence in an expanding universe. Nothing stays still. Everything moves, whether through gravitational attraction, cosmic expansion, or both. This brings us back to the strangeness of our situation. We're falling towards something we can barely see, pulled by gravity from mass we can't directly observe, following a trajectory determined by invisible dark matter distributed in ways we're only beginning to map. The destination, if you can call it that, lies hundreds of millions of light years away, so distant that we'll never actually reach it before cosmic expansion and Laniakea's eventual dispersal change the entire gravitational landscape. We're cosmic travelers on a journey with no fixed destination, following paths determined by forces we're still learning to measure and understand. And the strangest part, this journey started long before Earth existed and will continue long after it's gone. The Milky Way's trajectory through space preserves a record of cosmic history stretching back billions of years. Every gravitational interaction, every merger, every close encounter with another galaxy has left its signature in our motion. Dark matter halos remember their formation conditions. Stellar streams trace past galactic cannibalism. Peculiar velocities reveal the gravitational landscape through which we've traveled. Reading this history requires sophisticated techniques. Astronomers measure the positions and velocities of stars throughout the Milky Way, looking for patterns that reveal past disturbances. They map dark matter distribution using gravitational lensing. They simulate galaxy evolution on supercomputers, running the clock backward to reconstruct likely scenarios that produce the structures we observe today. What they've discovered is surprising. The Milky Way hasn't always been falling toward the great attractor. Billions of years ago, before Laniakea coalesced into its current form, our galaxy followed different gravitational currents. The cosmic web was less developed, superclusters less defined. The Milky Way moved through a universe where large-scale structure was still emerging from the slightly denser regions of the early universe. Back then, roughly 10 billion years ago, the gravitational landscape looked completely different. The great attractor region existed, but it was less massive, less concentrated. The Shapley supercluster was assembling from smaller precursor structures. The dipole repeller was forming as surrounding matter drained away toward more massive concentrations. The Milky Way's motion has been shaped by this evolving landscape. We've been deflected, accelerated, decelerated by passing structures. We've merged with smaller galaxies, absorbing their mass and momentum. Each interaction changed our trajectory slightly, nudging us onto new paths through the cosmic web. This raises a fascinating question. What determined the Milky Way's initial motion? Why were we moving in the direction we were moving when structure formation began? The answer traces back to quantum fluctuations in the incredibly early universe. During cosmic inflation, tiny quantum variations in density were stretched to macroscopic scales. These variations, imprinted in the cosmic microwave background, seeded all subsequent structure formation. Slightly denser regions attracted more matter. Slightly less dense regions repelled it. The Milky Way's current motion is the accumulated result of 13+ billion years of responding to this initial density field. We're still coasting on momentum imparted by quantum fluctuations that occurred when the universe was smaller than an atom. That's genuinely strange when you think about it. Your motion through space right now, the fact that you're falling toward the Shapley supercluster at over 2 million kilometers per hour, was determined by quantum randomness, in the first fraction of a second after the Big Bang. The dice were cast before the universe was a microsecond old, and we're still following the trajectory those random rolls determined. But there's a complication. Recent observations suggest our motion might be even stranger than this picture implies. In 2017, astronomers discovered the dipole repeller. This vast underdense region, lying in the opposite direction from the Shapley supercluster, contributes nearly as much to our motion as the Shapley attractor itself. We're not just being pulled toward mass, we're being pushed away from emptiness. The dipole repeller challenges our intuition about gravitational motion. We're used to thinking about gravity as attractive, pulling things together. Mass attracts mass. Simple. But in cosmology, underdense regions create effective repulsion. It's not that empty space pushes. Rather, when you're surrounded by mass in most directions, but there's a void in one direction, you get accelerated away from the void toward the mass. The net effect looks like repulsion, even though it's really just asymmetric attraction. The dipole repeller lies approximately 717 million light-years away in the opposite direction from Shapley. It's a supervoid, a region containing far fewer galaxies than average. Matter is drained out of this region, flowing towards surrounding attractors. What remains is a sparse cosmic desert. This discovery doubled the number of major influences on our motion. Previously, astronomers thought we were primarily responding to the pull from Shapley and the structures along the way. Now it appears we're equally influenced by the push from the dipole repeller. Our trajectory is the sum of these opposing forces. This creates a more complex picture of cosmic motion. Galaxies don't simply fall toward mass concentrations. They're simultaneously repelled by voids. The cosmic web isn't just shaped by where matter accumulates, but also by where it's absent. The empty spaces matter as much as the filled ones. Mapping this structure has been challenging. Voids don't emit light. You can't observe them directly. You infer their existence from the distribution of galaxies around them, from the way light bends around their edges, from the peculiar velocities of galaxies responding to their influence. The dipole repeller was discovered through velocity field mapping. Astronomers measured the peculiar velocities of thousands of galaxies, determining how fast they're moving relative to the cosmic expansion. They built computer models to explain these motions, searching for mass distributions that would produce the observed velocity patterns. The models kept requiring a significant underdensity in one direction to explain the data. Initially, this seemed like an artifact. Voids are common in the universe, but one this large in our immediate cosmic neighborhood seemed unlikely. Further analysis confirmed it was real. This changes how we understand our cosmic address. We don't just live in Laniakea falling towards Shapley. We live in a region bounded by Shapley on one side and the dipole repeller on the other. We're being squeezed between a massive attractor and a vast void, accelerated along the line connecting them. This configuration might not be coincidental. Structure formation tends to create alternating patterns of overdensity and underdensity. Mass flows out of underdense regions into overdense ones, creating a network of filaments, walls, and voids. The cosmic web resembles foam, with galaxies concentrated in thin sheets and filaments surrounding empty bubbles. Our location between Shapley and the dipole repeller places us in a typical position within this foam structure. We're in a sheet of matter bounded by voids, flowing along gravitational currents toward major mass concentrations. This is how most galaxies live, embedded in the cosmic web, responding to pushes and pulls from the large-scale structure surrounding them. But here's where it gets genuinely weird. Recent studies suggest our motion might be even faster than previously thought. In November 2025, researchers at Bielefeld University published an analysis suggesting our solar system is moving more than 3 times faster than the established models predict. If confirmed, this would challenge fundamental assumptions about large-scale structure and cosmic dynamics. The study examined the dipole in radio galaxy distributions, a different way of measuring our peculiar velocity. Instead of looking at galaxy motions directly, they mapped where radio-bright galaxies are located in the sky. The distribution shouldn't be uniform because we're moving, creating a dipole pattern with more galaxies appearing in the direction we're moving and fewer in the opposite direction. The measured dipole was far larger than expected. After accounting for all known factors, the data suggested we're moving at roughly 3 times the speed predicted by standard cosmological models. This is a 5.4 sigma result, meaning it's extremely unlikely to be statistical noise. If real, this discrepancy implies either our measurements contain systematic errors we haven't identified, or our understanding of large-scale structure needs revision. Maybe the distribution of mass in the local universe differs significantly from what models predict. Maybe dark matter is distributed differently than assumed. Maybe there are additional large-scale structures influencing our motion that we haven't detected. Alternative explanations include the possibility that radio galaxies aren't distributed uniformly, which would contaminate the measurement. Or perhaps our models of how galaxies form and evolve need adjustment, changing the predicted distribution in ways that affect the analysis. This remains unresolved. The finding is too recent and too surprising to have reached consensus. It requires independent confirmation using different methods and datasets. But if it holds up, it suggests our cosmic journey is even stranger than we realized. The possibility that we're moving significantly faster than models predict raises unsettling questions. What could cause such motion? What massive structures beyond our current observational reach might be influencing us? How much of the universe's gravitational landscape remains unmapped? These questions touch on fundamental limitations in our cosmic knowledge. We can only observe a finite volume of space. Beyond a certain distance, the universe's expansion carries objects away faster than their light can reach us. There's a cosmic horizon, a boundary beyond which we cannot see. This horizon limits what we can know about our motion. There might be massive structures beyond our observable universe pulling on everything we can see. We'd have no way to detect them directly. We'd only notice their influence through unexplained components of our motion, anomalies that models can't explain using visible structures alone. The 2025 velocity discrepancy might hint at such hidden influences, or it might simply reflect errors in our models or measurements. Distinguishing between these possibilities requires better data, more sophisticated simulations, and careful analysis of systematic uncertainties. What's certain is that our cosmic journey is more complex than early astronomers imagined. We're not simply orbiting the galactic center in a stable, predictable path. We're falling through a dynamic, evolving gravitational landscape. responding to influences from structures hundreds of millions of light years away, possibly being affected by mass beyond our observational horizon. This creates a humbling perspective. Every measurement we make, every map we construct, represents a snapshot of a dynamic, incompletely understood system. The universe we observe is a tiny fraction of what exists. Our motion through it is shaped by visible and invisible factors we're still learning to measure. The strangeness deepens when you consider dark matter's role in all this. Visible matter, the stuff that forms stars and glows in telescopes, comprises only about 15% of the total matter in the universe. The remaining 85% is dark matter, invisible except through its gravitational effects. This means the gravitational landscape guiding our motion is dominated by something we cannot directly observe. We map dark matter indirectly through gravitational lensing, through galaxy rotation curves, through computer simulations that match observed large-scale structure. But we're essentially navigating by feel, inferring the presence of massive invisible structures from their effects on visible matter. The great attractor region contains vast quantities of dark matter. The dipole repeller is a void in both visible and dark matter. The filaments connecting superclusters are dominated by dark matter halos. Our entire trajectory through space is determined primarily by the distribution of something we've never directly detected. Recent simulations reveal another layer of strangeness. In March 2026, researchers published findings showing that our local group sits in a gigantic flat sheet of matter, surrounded by enormous voids above and below. This local sheet extends tens of millions of light years, with the Milky Way and nearby galaxies embedded within it. This sheet structure is dominated by dark matter. The visible galaxies are just tracers marking the locations of much more massive dark matter concentrations. The sheet's geometry balances gravitational forces in complex ways, explaining peculiar motions of nearby galaxies that previously seemed anomalous. For galaxies in the sheet, the gravitational pull from the local group is counteracted by pull from more distant mass in the plane. The voids above and below create effective repulsion perpendicular to the sheet. The result is that galaxies within the sheet experience different gravitational forces than they would in a more uniform distribution. This matters for understanding our motion because it affects how local gravitational influences combine with large-scale flows towards Shapley and away from the dipole repeller. We're not moving through a smooth, uniform universe. We're embedded in a structured environment where local geometry affects how we respond to distant attractors. The strangeness compounds. We're falling towards something we can barely observe, pushed by emptiness we can't directly see, guided by dark matter we've never detected, moving through a sheet-like structure revealed only through sophisticated simulations, possibly influenced by structures beyond our observational horizon, traveling at speeds that might challenge our theoretical models. And all of this was set in motion by quantum fluctuations 13 billion years ago. The initial conditions of the universe, the quantum fluctuations in the first fraction of a second after the Big Bang, contain the seeds of everything that followed. Those microscopic variations in density, stretched to cosmic scales by inflation, determined where galaxies would form, where voids would emerge, where massive structures would coalesce. Your current trajectory towards Shapley, your position within the local sheet, your motion away from the dipole repeller. All of this was encoded in patterns established when the universe was smaller than an atom. The path you're following was laid down 13 billion years before Earth existed. This raises profound questions about determinism and cosmic evolution. How much of the universe's large-scale structure was inevitable, locked in by those initial conditions? How much emerged from the complex interplay of gravity, dark matter, and dark energy over billions of years? Recent simulations suggest the answer lies somewhere between complete predetermination and chaotic unpredictability. The broad strokes were set early. The general pattern of filaments, walls, and voids emerged from the distribution of matter and dark matter in the early universe. But the details, the specific shapes and sizes of individual structures, evolved through processes that amplified small differences over cosmic timescales. Your motion through this landscape reflects both aspects. The general direction toward Shapley was probably inevitable given the distribution of mass in this region of the universe. But the specific velocity, the exact trajectory, the influence of intermediate structures like the great attractor, these emerge from billions of years of gravitational interactions. This connects to something even stranger about your cosmic journey. You're not just moving through space, you're moving through time in a very specific way that relates to your velocity. Einstein's relativity tells us that time passes differently for objects moving at different speeds. The faster you move, the slower your clock ticks relative to stationary observers. At everyday speeds, this effect is negligible. But at cosmic velocities, it becomes measurable. The Milky Way is moving at 631 kilometers per second relative to the cosmic microwave background. That's over 2 million kilometers per hour. At this speed, time dilation effects are tiny but real. Your clock runs slower than it would if you were stationary relative to the CMB by about 1 part in several trillion. This seems trivial until you consider the timescales involved. Over billions of years, these tiny differences accumulate. The Milky Way has been in motion since its formation roughly 13 billion years ago. During that time, the cumulative time dilation effect amounts to thousands of years. Think about what this means. If there's a galaxy somewhere that's been stationary relative to the CMB for the past 13 billion years, which is impossible, but bear with me, then that galaxy has experienced about 10,000 more years of cosmic time than we have. Our motion through space has literally stolen thousands of years from our timeline. This gets even stranger when you consider galaxies moving at different velocities in different directions. Galaxies falling towards Shapley at different rates are experiencing time at different rates. The cosmic web isn't just a spatial structure, it's a temporal structure, with different regions of space aging at slightly different rates depending on their motion through the universe. Your trajectory towards Shapley means you're experiencing time differently than galaxies moving in other directions or at other speeds. The universe isn't just spatially heterogeneous, it's temporally heterogeneous, with the flow of time varying subtly from place to place based on local velocities. Now, layer on gravitational time dilation. Einstein also showed that time passes more slowly in stronger gravitational fields. Near massive objects, clocks tick slower than they do in empty space. As you fall towards Shapley, you're falling into progressively stronger gravitational fields. Not just from Shapley itself, but from all the intervening structures along your path. Each galaxy cluster you approach, each filament you traverse, affects how time passes for you relative to observers in less dense regions. The combination of velocity-based time dilation and gravitational time dilation creates a complex temporal landscape overlaying the spatial structure of the cosmic web. Different regions of the universe are aging at different rates, not just because of the universe's expansion, but because of their motion and position within the gravitational field of large-scale structure. This has implications for understanding cosmic evolution. When we observe distant galaxies, we're not just seeing them as they were in the past because their light took time to reach us. We're seeing them as they were when they had experienced a different amount of proper time than we have, based on their different trajectories through space and their different positions in the cosmic gravitational field. The universe's history isn't a single timeline. It's a bundle of timelines, all slightly offset from each other based on local conditions. Your motion towards Shapley places you on one particular timeline among countless others threading through the cosmos. But here's where the strangeness reaches a new level. Recent observations suggest something even more peculiar about our motion. Remember that 2025 study from Bielefeld University suggesting we might be moving more than 3 times faster than expected. That measurement, if confirmed, doesn't just challenge our understanding of local structure. It challenges our understanding of how velocities arise in an expanding universe. In standard cosmology, peculiar velocities, the motions of galaxies relative to the Hubble flow, arise from gravitational interactions with nearby mass concentrations. You can calculate expected velocities based on the distribution of visible and dark matter within a few 100 million light-years. But if we're moving significantly faster than those calculations predict, it suggests one of several possibilities. Either there's more mass nearby than we've detected, hidden perhaps in dark matter structures we haven't mapped, or the gravitational influence extends from much more distant structures than we thought, implying the universe's matter distribution differs from our models on very large scales, or our understanding of how gravity works on cosmic scales needs revision. Each possibility is profound. Hidden nearby mass would mean our maps of the local universe are fundamentally incomplete. Long-range gravitational effects would require rethinking how cosmic structure formation works. Modified gravity would overturn general relativity's predictions in certain regimes. The excess velocity might also relate to structures beyond our current observational horizon. If there are massive concentrations of matter beyond what we can currently observe, their gravitational influence could still affect us, pulling us in directions that seem anomalous based only on visible structure. This connects to a deep question in cosmology. How far does gravitational influence extend? In principle, every mass in the universe gravitationally affects every other mass, but in practice, the expansion of space dilutes these effects over large distances. There should be some scale beyond which distant structures have negligible influence on local motions. But what if that scale is larger than we thought? What if structures hundreds of millions or even billions of light-years away contribute meaningfully to our motion? This would mean our trajectory is shaped not just by our local neighborhood within Laniakea, but by the distribution of matter throughout a much larger volume of space. Recent analyses of bulk flows support this possibility. Observations show coherent motions of galaxy groups extending to distances of 250 megaparsecs or more. That's over 800 million light-years. These bulk flows suggest gravitational influence from structures at the edge of, or even beyond, our current surveys. Your motion towards Shapley might not be driven solely by Shapley and the intermediate structures between here and there. It might be influenced by mass distributions extending far beyond, in regions we haven't yet properly mapped or even detected. This creates an observational challenge. To fully understand why we're moving the way we are, we need to map the universe's structure out to distances where gravitational influence becomes negligible. But we don't know in advance how far that is. We might need to survey volumes much larger than we currently have to fully account for observed motions. The 2025 velocity discrepancy might be telling us we haven't surveyed far enough. There might be massive structures lurking beyond our current observational limits, pulling us in ways we haven't accounted for because we haven't seen them yet. This brings us back to the zone of avoidance. That 10% of the sky blocked by the Milky Way's dust and stars isn't just an inconvenient observational gap. It's a critical blind spot that might hide structures essential for understanding our motion. The Great Attractor lies partially within the zone of avoidance. The Norma cluster, identified as the gravitational center of that region, was discovered only after extensive infrared and radio surveys that could penetrate the obscuring dust. But how much more remains hidden? Recent surveys using neutral hydrogen mapping and other techniques that penetrate the zone have discovered hundreds of previously unknown galaxies. The Vela supercluster, a massive structure influencing our motion, was largely hidden until these surveys revealed its extent. What else might be lurking in that obscured region? Could there be structures massive enough to significantly affect our trajectory that we simply haven't detected because they're hidden behind the galactic plane? This is particularly relevant for understanding our motion, because the zone of avoidance lies roughly in the direction of our motion. We're heading toward a region we can't fully observe. It's like navigating through fog, inferring what's ahead from indirect measurements and gravitational effects rather than direct observation. The South Pole Wall, discovered recently, illustrates how much we're still learning about nearby structure. This enormous wall of galaxies, as large as the Sloan Great Wall, lies just beyond Laniakea, wrapping around it like an arm. It was discovered only through painstaking analysis of redshift surveys and peculiar velocity measurements. The South Pole Wall extends across 200 degrees of the sky, reaching from Earth's south pole well into the northern hemisphere. Parts of it lie within 300 million light-years of the Milky Way, yet it remained undetected until 2020 because much of it lies in regions difficult to survey, either due to the zone of avoidance or the crowded galactic plane. Researchers describe themselves as early explorers of the cosmos, extending maps into unknown territory. The mapped portions of the South Pole Wall stretch across the full domain of surveyed regions, suggesting it might extend even further into unsurveyed areas. We don't know its full extent. We don't know its total mass. We don't know how significantly it influences our motion. This uncertainty pervades our understanding of cosmic structure. Every major survey discovers new structures, new walls, new voids, new superclusters. Each discovery refines our understanding of the gravitational landscape guiding our journey. Each also reveals how much remains unknown. Your trajectory towards Shapley threads through this incompletely mapped landscape. The path seems clear from what we've observed, but significant structures might remain hidden, waiting to be discovered. potentially altering our understanding of why we're moving the way we are. This is where the strangeness of our situation becomes almost overwhelming. We're falling through space at enormous velocities, driven by the gravitational influence of structures both visible and invisible, some observed, some inferred, some potentially still unknown. We're moving through a universe where 85% of the matter is dark, where 68% of the energy is even more mysterious dark energy, where significant regions of nearby space remain obscured, where recent measurements suggest we might be moving faster than our models predict. We're navigating by incomplete maps through a landscape we don't fully understand, toward a destination 650 million light-years away that we can barely observe, influenced by structures we've never directly detected, possibly affected by mass beyond our observational horizon. And this has all been happening since long before humans existed, long before Earth formed, long before the Sun ignited. The Milky Way has been falling towards Shapley for billions of years, following a trajectory established by the initial conditions of the universe and shaped by the evolving distribution of matter and dark matter across cosmic time. You're part of a journey that began before the solar system existed and will continue long after the sun dies. A journey through space and time, shaped by visible and invisible forces, following paths determined by the architecture of the universe itself. The strangeness isn't just that we're moving towards something, it's that the something we're moving toward is embedded in a cosmic structure far more complex, far more mysterious, and far more incompletely understood than we might have imagined. Yet beneath these uncertainties lies something even more unsettling, something that challenges our fundamental assumptions about how the universe works. Dark energy. We've mentioned it briefly, but now we need to confront what it means for this cosmic journey we're on. Because dark energy isn't just accelerating the expansion of the universe in some abstract way. It's actively working against everything we've been discussing. Every gravitational structure we've explored, Laniakea, the great attractor, Shapley, exists because gravity has pulled matter together over billions of years. Structure formation depends on gravity's ability to overcome the universe's expansion, creating islands of increasing density in an expanding sea of space-time. Dark energy opposes this process. It's causing space itself to expand at an accelerating rate. The farther apart objects are, the faster space expands between them. On small scales, gravity easily overcomes this expansion. Your body isn't expanding, Earth isn't expanding, even our galaxy isn't expanding, held together by its own gravity. But on larger scales, dark energy wins. And here's what makes our situation so strange. Laniakea itself is not gravitationally bound. Despite containing 100,000 galaxies, despite spanning 500 million light-years, despite being defined by coherent flows toward the great attractor, Laniakea is temporary. Dark energy will tear it apart. The supercluster we've been calling our cosmic home is doomed. Not in the dramatic sense of a collapse or explosion, but through gradual dispersal, as the expansion of space overcomes the gravitational ties that currently create coherent motion. Computer simulations show this clearly. Laniakea's constituent superclusters will drift apart. The flows that currently define its structure will weaken. Eventually, the gravitational basin that makes it a meaningful entity will cease to exist. How long do we have? Estimates vary, but we're talking tens of billions of years. Long after the sun dies, long after most stars currently burning have exhausted their fuel. But it will happen. Now think about what this means for the journey toward Shapley. We're falling through space at 630 kilometers per second, drawn by gravitational attraction that will eventually lose its battle against cosmic expansion. Will we reach Shapley? Will the Milky Way complete this billion-year journey toward the most massive concentration of matter in the local universe? The answer depends on timescales, on the precise rate of cosmic expansion, on how dark energy's influence grows over time. Current models suggest we won't. The expansion will win before we arrive. We're falling towards something we'll never reach. Think about that for a moment. This entire cosmic story, the great attractor, the dipole repeller, the Shapley concentration pulling us across hundreds of millions of light years, represents a journey that will never be completed. We're passengers on a train that will never arrive at its destination because the tracks themselves are being pulled apart faster than we can travel them. But the strangeness goes deeper. Remember those 2025 findings from Bielefeld University? The observations suggesting we might be moving 3 times faster than expected relative to the cosmic microwave background. If confirmed, this doesn't just mean our models need adjustment. It suggests something fundamentally unexpected about the large-scale structure of the universe or the distribution of matter within it. One possibility: there's more structure we haven't detected, more mass influencing our motion. Perhaps beyond Shapley, perhaps in directions we haven't fully surveyed, there exist even more massive concentrations pulling at us. Another possibility: our understanding of how structure formed in the early universe needs revision. Maybe the initial conditions produced larger density fluctuations than our models predict. Maybe dark matter distributed itself differently than we assume. A third possibility: something about our cosmological model itself is incomplete. Maybe dark energy behaves differently than we think. Maybe gravity operates slightly differently on cosmic scales. Maybe there's physics we haven't discovered yet. Each possibility opens onto vast unknowns, and we're confronted again with the fundamental limitation. We can only observe a finite portion of the universe. The cosmic horizon, determined by the speed of light and the universe's age, sets an absolute boundary on what we can see. Beyond that horizon, more universe exists, more structure, more matter, more galaxies and clusters and superclusters we'll never observe because their light hasn't had time to reach us. Could there be structures beyond our horizon influencing our motion? Gravitational effects that reach across cosmic distances, pulling at us from regions we'll never see. Theoretically, yes. Gravity, unlike light, isn't limited by when the universe became transparent to radiation. Gravitational influences can potentially extend from beyond the observable universe, affecting matter within our horizon. We might be feeling the pull of structures we can never observe. That's a profound uncertainty. Our cosmic journey might be shaped by invisible architects we cannot study, cannot measure, cannot verify. Forces from beyond the edge of observation guiding us toward destinations we'll never reach. But let's return to something more concrete. Something happening right now in our immediate cosmic neighborhood. The local sheet. Those 2026 simulations revealed something remarkable about our local environment. The mass distribution within about 33 million light-years of the local group isn't random. It's organized into a flat structure, a vast plane of matter, with enormous voids above and below. This sheet includes both visible galaxies and the dark matter halos surrounding them. The simulations show this structure is necessary to explain the observed motions of nearby galaxies. Without it, the mathematics don't work. Here's what makes this fascinating. The local sheet creates a gravitational balance. Nearby galaxies within this sheet feel gravitational pull from the local group in one direction and pull from more distant mass in the sheet in the opposite direction. These forces roughly balance, allowing galaxies to drift outward from the local group even though they're gravitationally influenced by it. The sheet's geometry creates a kind of gravitational equilibrium that permits motion we wouldn't otherwise expect. This is dark matter architecture made visible through its effects. We can't see the dark matter directly, but we can infer its distribution by observing how galaxies move. The local sheet is dominated by dark matter. Roughly 85% of its mass is invisible, but its structure shapes the behavior of visible matter in profound ways, and we're embedded in it. The Milky Way sits within this vast plane, surrounded by voids, part of a structure that extends for tens of millions of light years. It's like discovering your house sits on a geological formation you never knew existed. The ground beneath you has structure, history, implications you never considered. The local sheet is our immediate cosmic geography. But it's also a small feature within Laniakea, which is itself being pulled towards Shapley, which exists within an even larger structure we're still mapping. Layers within layers, structures within structures, motion within motion. Your trajectory through space reflects all of these nested influences simultaneously. You're rotating with Earth, orbiting with Earth around the Sun, moving with the Sun around the galactic center, falling with the Milky Way through the local sheet toward the great attractor, flowing with Laniakea towards Shapley, all while being pushed by the dipole repeller and influenced by dark energy pulling the universe apart. Each motion occurs at different scales, different speeds, different timescales. Some you complete many times in a human lifetime. Others will continue for billions of years, long after humanity has vanished, long after Earth has been consumed by the dying sun, long after the last stars have formed. You're part of a cosmic dance choreographed by gravity, shaped by the initial conditions of the universe, modified by 13.8 billion years of structure formation, and ultimately doomed by the accelerating expansion driven by dark energy. But here's something worth considering. This journey, our fall through space towards Shapley, our motion through Laniakea, our position within the local sheet, represents a specific moment in cosmic history. If you could observe the universe from outside, watching billions of years pass in accelerated time, you'd see structure formation as a dynamic process. Galaxies falling together, clusters merging, superclusters organizing. Then, as dark energy's influence grows, you'd see the process reverse. Structures dispersing, clusters separating, superclusters dissolving. We exist during the brief cosmic moment when structure has formed but hasn't yet dispersed, when gravity has created organized flows and coherent superclusters, but dark energy hasn't yet torn them apart. This is a temporary state, a phase in cosmic evolution. In the deep future, assuming dark energy continues accelerating expansion, galaxies will become isolated islands in an expanding sea. The local group, if the Milky Way and Andromeda do merge, will find itself alone. Other galaxies will recede beyond the cosmic horizon, disappearing from view as space expands faster than their light can reach us. Future astronomers, if they exist, will observe a universe very different from ours. They'll see only their local galaxy or merged galaxy cluster. The cosmic microwave background will have redshifted to undetectable wavelengths. Evidence of the Big Bang will be harder to find. The expansion of the universe might be impossible to measure directly. They'll inhabit a universe that appears static, eternal, unchanging. They'll have no way to know about Laniakea, about Shapley, about the great structures and flows that dominated the cosmos during our era. They might not even realize the universe had a beginning. This makes our cosmic moment precious. We exist during the window when the universe's history is still observable, when structure is coherent, when the great cosmic flows can still be measured and mapped. We're privileged observers of a phase that will end, and we're participants in motion we'll never complete, falling toward a destination we'll never reach, part of structures that will eventually dissolve, witnessing a universe in the brief interval between its structured past and its dispersed future. The strangeness of what Earth is moving toward isn't just about Shapley or the great attractor or dark matter or any single feature of cosmic structure. The strangeness is about existing during this specific moment in cosmic evolution, observing processes that will never finish, measuring motions that expansion will ultimately overcome, mapping structures that are already beginning to dissolve, even as gravity still shapes their flows. We're watching the universe in transition, from structured to dispersed, from gravitationally dominated to expansion dominated, from observable to hidden, and we're part of that transition, falling through space at 630 kilometers per second towards something we're only beginning to understand, influenced by forces both visible and invisible, moving through a landscape both mapped and mysterious on a journey measured in billions of years that will never reach its end. What does this mean for understanding our cosmic address? Our position in the universe is defined not by static coordinates, but by motion, by flows, by the gravitational currents that carry us through space at speeds we can barely measure. The Milky Way isn't located at a specific point in the cosmos. It's located within a velocity field, embedded in the gravitational landscape, shaped by matter both visible and invisible. Our address isn't a position, it's a trajectory. This is fundamentally different from how we typically think about location. When someone asks where you live, you give a street address, a city, a country, fixed coordinates on a map. But galaxies don't have fixed coordinates. The universe is expanding, space itself is stretching, and within that expansion, gravitational structures create currents and flows that define our cosmic neighborhood more accurately than any coordinate system could. The local sheet, Laniakea, the great attractor, Shapley. These aren't just interesting features of large-scale structure. They're the framework that determines where we are and where we're going. They define our cosmic context as surely as continents and oceans define geography on Earth. And this framework is temporary, not just because dark energy will eventually disperse it, but because it's actively evolving right now. The flows we measure today aren't the same as the flows that existed 1 billion years ago or that will exist 1 billion years hence. Cosmic structure is dynamic, changing, reorganizing itself on timescales so vast they're difficult to comprehend. Consider what this means for our understanding of cosmic time. We measure the universe's age at 13.8 billion years. We calculate when structures formed, when galaxies merged, when stars ignited. But we rarely think about where we are in the story of structure formation, what chapter we're observing. The answer is late middle, maybe even early late. The universe has transitioned from smooth to structured, from simple to complex, from uniform to organized. We exist after that transition has largely completed, but before the next transition, from structured to dispersed, has fully begun. We're in the brief interval when gravity has won but hasn't yet lost, when structure exists but is already beginning to fade. The flows we measure, the attractors that pull us, the sheets and voids that organize our neighborhood, all of this represents the high watermark of cosmic structure. The moment of maximum organization before dark energy's influence grows strong enough to reverse the process. And we're participants in that moment, not just observers. We're being carried by these flows. Our galaxy is part of this structure. Our solar system, our planet, everything we've ever known exists within the gravitational currents that define this cosmic era. Now here's something that should make you pause. The motion we've been discussing, 630 kilometers per second toward Shapley, 600 kilometers per second toward the great attractor, represents peculiar velocity, motion that deviates from the Hubble flow, motion caused by gravitational structure rather than cosmic expansion. But there's another component to our motion, one that's far faster and far stranger. The Hubble flow itself is carrying us away from distant structures at speeds that increase with distance. Galaxies 1 billion light-years away are receding from us at roughly 23,000 kilometers per second. Not because they're moving through space, but because space itself is expanding between us and them. This creates a bizarre situation. We're falling towards Shapley at 630 kilometers per second due to gravity. But Shapley is simultaneously being carried away from us by the expansion of space. At Shapley's distance, 650 million light-years, the expansion rate is roughly 15,000 kilometers per second. We're chasing something that's fleeing faster than we're approaching. The mathematics of this is straightforward, but the implications are profound. Our peculiar velocity towards Shapley will never overcome the expansion of space. We're falling toward a destination we cannot reach, running on a cosmic treadmill where the destination moves away faster than we can approach. This is true for all large-scale structure. The flows within Laniakea, the attraction toward Shapley, the influence of the great attractor, all of these gravitational effects are real and measurable, but they're all occurring within an expanding universe that will ultimately separate the structures they're trying to pull together. Gravity is losing. Not immediately, not on human timescales or even galactic timescales, but on cosmic timescales, dark energy wins. Expansion overcomes attraction. Structure disperses. The flows we measure today are fossil remnants of a universe that was once more conducive to structure formation. When the universe was younger and denser, when dark energy's influence was weaker, gravity could overcome expansion and pull matter together into galaxies, clusters, and superclusters. But that era is ending. Dark energy's influence grows as the universe expands. Eventually, tens of billions of years from now, it will overcome all gravitational binding except within the very smallest structures. Galaxy clusters will disperse. Superclusters will dissolve. The cosmic web will unravel. And the flows we're measuring now, the motion toward Shapley and the great attractor, will become meaningless. relics of an earlier cosmic age when structure still dominated. So when we ask what Earth is moving toward, the answer has layers. Immediately, we're orbiting the Sun. On a longer timescale, we're orbiting the galactic center. Over even longer periods, we're falling toward the great attractor, toward Shapley, toward the densest regions of our local universe. But ultimately, we're moving toward isolation, toward a future where the local group, or whatever merged structure it becomes, exists alone in an expanding void, where other galaxies have receded beyond the cosmic horizon, where the evidence of cosmic structure has faded into the stretched wavelengths of undetectable radiation. This is the strangest part. Not the current motion, but the ultimate destination. We're moving toward emptiness, toward cosmic loneliness, toward a universe that appears very different from the one we observe today, and there's no escaping this fate, no way to overcome it. The expansion of space isn't something you can fight with rockets or warp drives, or any conceivable technology. It's not motion through space. It's the creation of new space between existing points. And dark energy ensures this process accelerates. Every second, the universe grows larger. Every moment, distant structures recede further beyond reach. The cosmic horizon shrinks. The observable universe becomes smaller, even as the actual universe grows larger. This creates a peculiar situation for cosmic understanding. We exist during the brief window when the universe's history is still visible, when the cosmic microwave background is still detectable, when distant galaxies can still be observed, when the evidence of the Big Bang and cosmic evolution remains accessible. Future civilizations, if they exist, will inhabit a very different cosmos. They'll see only their local galaxy or merged galaxy cluster. The rest will have disappeared beyond the horizon. They'll have no way to discover the Big Bang, no evidence of cosmic expansion, no ability to map large-scale structure. They'll think they live in a static, eternal, unchanging universe. And they'll be wrong. But they'll have no way to know they're wrong. We're lucky. We exist during the era when cosmic history remains visible, when the flows and structures that shaped our universe can still be measured and mapped, when the story of how we got here can still be read in the light from distant galaxies. But this luck is temporary. The window is closing, not on human timescales, but on cosmic ones. The universe we observe today is not the universe that will be observed in the deep future. So what is Earth moving toward? Toward Shapley, toward the great attractor, toward the densest regions of local structure, but also toward isolation, toward a future where these destinations have receded beyond reach, toward a cosmos fundamentally different from the one we inhabit. The strangeness isn't just in the motion itself. It's in the fact that this motion is simultaneously real and futile. We're falling towards something we'll never reach, influenced by structures that are already beginning to disperse. Participants in flows that expansion will ultimately overcome. And perhaps that's the deepest lesson. The universe doesn't exist in a static state. It's not a fixed stage where events unfold. It's dynamic, evolving, transitioning from one era to another. We're privileged to exist during the structured era. When galaxies cluster, when superclusters organize, when gravitational flows create coherent motion across hundreds of millions of light years. This won't last forever. It's already ending. The motion we measure, our fall through space at 630 kilometers per second, is evidence of a universe in transition from smooth to structured, from structured to dispersed, from observable to hidden. We're watching structure formation in its final act, measuring flows that will never complete, mapping a cosmic landscape that's already beginning to fade, and we're part of it. Every atom in your body is participating in this cosmic motion. You're moving through space at speeds that would have been unimaginable to previous generations. You're embedded in gravitational flows shaped by dark matter structures we've only recently begun to map. You're a temporary arrangement of matter caught in the vast currents that connect the local sheet to Laniakea to Shapley to the largest structures in the observable universe. This is what Earth is moving toward. Not just a destination, but a cosmic fate. Not just a location, but a cosmic fate. Not just a location, but a future. Not just structure, but the eventual absence of structure. The universe is taking us somewhere, carrying us along gravitational highways shaped by 13.8 billion years of evolution. And simultaneously, it's taking that destination away. Stretching space, accelerating expansion, ensuring we'll never arrive. That's the strange part. Not the motion, not the speeds, not the structures. The strange part is that we're on a journey with no end, falling towards something that's falling away, part of flows that will never reach their destination, participants in a cosmic story that's already beginning to erase its own history. You're moving at 630 kilometers per second through a universe that's simultaneously pulling you forward and pushing you away, being drawn toward massive structures while fleeing from cosmic voids, embedded in sheets of dark matter you can't see, influenced by forces you can't directly measure, following trajectories established by quantum fluctuations that occurred when the universe was smaller than an atom. And here's what might be the strangest realization of all. This motion has no observer except you. No cosmic reference frame marks your passage. No universal clock measures your journey. You're moving relative to the cosmic microwave background, relative to the great attractor, relative to Shapley. But there's no absolute motion, no universal stillness against which your velocity can be measured. Einstein showed us this over a century ago. Motion is always relative, always depends on your frame of reference. There's no privileged perspective from which to declare something truly at rest. This means your motion toward Shapley is real and measurable, but it's not absolute. Someone in a different galaxy, moving in a different direction, would measure different velocities, calculate different flows, map different gravitational landscapes. The universe doesn't have a single story of motion. It has countless stories, one for each possible observer, each equally valid, each revealing different aspects of cosmic structure. Your story is falling towards Shapley at 630 kilometers per second. Another galaxy's story might be falling toward a different attractor. A third might be riding the expansion with minimal peculiar velocity. Each story is true from its own perspective, but they all share something fundamental. They're all temporary, all part of a universe transitioning from one state to another. All participants in structure formation's final act before dark energy disperses what gravity has built. This creates an unusual emotional response when you truly grasp it. Not fear exactly, not wonder alone, something more complex. A recognition that you're part of something vast and ancient and doomed, that your cosmic address is temporary, that the flows carrying you will eventually cease, that the structures defining your neighborhood will dissolve. Ah, but also a recognition that right now, in this cosmic moment, those structures exist. Those flows are real. That motion is happening. You're part of the greatest gravitational experiment in the universe, the formation and evolution of cosmic structure across billions of light years and billions of years. The Milky Way has been falling toward Shapley since before Earth existed, will continue falling long after Earth is gone. Your participation in this journey is brief, your awareness of it even briefer. But the journey itself spans cosmic time. Think about the layers of ignorance that have peeled away. Ancient humans thought Earth was stationary at the center of creation. Copernicus showed we orbit the sun. Shapley, different Shapley, showed the sun orbits the galactic center. Hubble showed the universe is expanding. Modern astronomy reveals we're falling through that expansion toward massive structures shaped by invisible dark matter. Each discovery revealed motion we didn't know we had. Each layer of understanding showed us moving faster on larger scales, through more complex landscapes than we'd imagined. What motion remains undiscovered? What influences haven't we measured? The 2025 findings suggesting we might be moving 3 times faster than expected hint that we're still missing something, still incompletely mapping the gravitational landscape, still discovering the full complexity of our cosmic trajectory. Perhaps there are structures beyond our current horizon influencing us. Perhaps dark matter distributes itself in ways we haven't modeled. Perhaps gravity operates slightly differently on cosmic scales than general relativity predicts. We don't know. And that uncertainty is both frustrating and exhilarating. Frustrating because we want complete understanding. Exhilarating because it means discovery remains possible. The map isn't finished. The story isn't complete. Every new survey discovers structures we didn't know existed. Every improved measurement refines our understanding of cosmic flows. Every simulation reveals new complexity in how matter organizes itself across cosmic time. The zone of avoidance still hides structures we can't observe. The dipole repeller's full extent remains unmapped. The South Pole wall might extend far beyond currently surveyed regions. Dark matter's detailed distribution throughout Laniakea needs better mapping. Each unknown represents opportunity. Each uncertainty points toward future discoveries that will refine our understanding of where we're going and why. But beneath all this complexity, beneath the uncertainties and the incomplete maps and the contested measurements, lies a simple fact. You're moving, right now, as you process these words, through space at speeds that would cross the distance from Earth to the Moon in minutes, carried by gravitational currents shaped by the largest structures in the universe, part of flows that began billions of years ago and will continue billions of years hence. This motion defines your cosmic context as surely as your location on Earth's surface defines your terrestrial context. You're not just on a planet orbiting a star in a galaxy. You're in the local sheet within Laniakea, falling toward the Shapley concentration, pushed by the dipole repeller, embedded in dark matter structures we're only beginning to map. Your cosmic address is a velocity field, a position within gravitational flows, a trajectory through space-time shaped by matter, both visible and invisible, by forces both measured and inferred, by structures both observed and hidden. And that address is changing, not just because you're moving through it, but because it's moving through cosmic time. The structures around you are evolving. The flows are shifting. The gravitational landscape is transforming as matter continues clustering and dark energy continues accelerating expansion. The universe you inhabit today isn't the universe that existed 1 billion years ago or that will exist 1 billion years hence. The cosmic address you occupy is temporary, specific to this moment in cosmic evolution. But it's your moment, your cosmic context, your place in the grand structure of space-time. Perhaps that's the most important realization. Not the specific velocity or the exact destination or the precise mass of the great attractor, but the fact that you exist during this brief window when cosmic structure is still forming, still observable, still shaping the motion of galaxies across hundreds of millions of light years. You're privileged to inhabit a universe where the story of structure formation can still be read, where the flows and currents that connect the smallest scales to the largest remain accessible to measurement, where the evidence of cosmic evolution hasn't yet been erased by expansion. Future beings, if they exist, won't have this privilege. They'll inhabit isolated galaxies in an apparently empty universe. The cosmic microwave background will have faded beyond detection. Evidence of the Big Bang will be harder to find. The flows we measure today will have ceased. They'll think they live in an eternal, unchanging cosmos. They'll be wrong, but they'll have no way to know it. You know differently. You exist during the era when cosmic truth remains visible, when the universe's history can still be reconstructed, when the structures shaping your motion can still be mapped and measured. That makes this moment precious, not in a sentimental sense, but in a cosmic one. The universe you observe is temporary. The structures you measure are transitional. The flows you're part of represent a specific phase in cosmic evolution that won't last forever. So when you look up at the night sky, when you contemplate your place in the cosmos, remember this. You're not stationary. You're not even simply orbiting the galactic center. You're falling through space at 630 kilometers per second towards something so massive it influences motion across hundreds of millions of light years. Being pushed by cosmic voids, guided by dark matter structures, carried by gravitational currents established billions of years ago, you're part of the greatest motion in the universe. Not the expansion of space itself, but the flows within that expansion. The organized currents that connect local sheets to superclusters, to the largest gravitational structures in the cosmos. And you're part of it right now. Every second, you travel 630 kilometers closer to Shapley. Every hour, over 2 million kilometers. Every day, 54 million kilometers. The motion never stops, never pauses, never slows. You're on a cosmic journey measured in billions of years toward a destination you'll never reach, influenced by forces both seen and unseen, part of structures both mapped and mysterious, moving through a universe in transition from structured to dispersed, from observable to hidden, from the era when gravity still shapes large-scale flows, to the era when dark energy tears those flows apart. This is what Earth is moving toward. Not just Shapley or the great attractor or any single destination, but toward a future fundamentally different from the present. Toward isolation in an expanding cosmos. Toward the dissolution of the very structures currently shaping your trajectory. You're watching structure formation in its final act, participating in gravitational flows that represent the high watermark of cosmic organization. Existing during the brief moment when the universe is complex enough to create structures like Laniakea, but not yet dispersed enough to dissolve them completely. The strangeness isn't just in the motion itself, it's in the context, the cosmic phase, the temporary nature of everything you're part of. You're moving through a universe that's simultaneously building structures and beginning to tear them apart, being pulled by gravity while expansion pushes back, falling toward destinations that are simultaneously receding beyond reach. And perhaps that's the deepest truth. The universe isn't static, isn't fixed, isn't eternal in any simple sense. It's dynamic, evolving, transitioning through phases that each last billions of years but are temporary nonetheless. Your motion through space reflects that evolution, carries the signature of cosmic history from quantum fluctuations in the early universe to the present-day structures shaped by dark matter and dark energy. Tells a story of how matter organized itself over cosmic time and how that organization will eventually disperse. Every atom in your body participates in this story. Every molecule, every cell. You're not separate from cosmic motion. You're part of it. A temporary arrangement of matter caught in gravitational currents that span the observable universe. Right now, you're moving at 630 kilometers per second towards something stranger than you might have imagined. Not just a massive structure or a distant destination, but toward a cosmic future where the very concept of large-scale structure has different meaning, where the flows we measure today have ceased, where the universe has transitioned to its next phase. You're a witness to cosmic evolution, a participant in structure formation's final chapter, a temporary observer of a temporary phenomenon. Your cosmic moment is brief, but it's real, measurable, profound. And it's happening right now, whether you feel it or not, as you continue your journey through space at speeds that dwarf anything humans have ever achieved, guided by forces we've only recently learned to measure, toward destinations we're only beginning to understand. Part of the vast cosmic dance that began with the Big Bang and will continue until the last structures dissolve into the expanding void.